Okay, so we've done some specific heat capacity calculations, and we've shown how if you've got a hot metal, that metal can transfer its heat into the water, and we can calculate what metal we have by finding the specific heat of the metal. Now we're going to talk about how would you do that if you had a ham sandwich. If you wanted to know the energy in a ham sandwich, and believe me, you all have worried about energy in things because that's what calories are. Have you ever wondered, where do we get the calories that are in food? Where does that come from? We had a big joke about this when I was in high school. So they have what's called a bomb calorimeter. And a bomb calorimeter is a big canister, and inside it has a chamber, and the chamber has a place where you can have a reaction occur. So imagine you want to know the energy in your ham sandwich. Well, you're going to put it into this chamber. There are electrodes that run down into it, and you would ignite those electrodes. There's oxygen in the chamber, and you get a reaction, and the ham sandwich would burn. The energy would then be given off into the water, and the water temperature would raise. That is what we're talking about when we talk about a bomb calorimeter. And we just thought it was really funny because the name was bomb calorimeter, and you could put a ham sandwich in it. I don't think you really would put a ham sandwich in it. I think that our chemistry teacher thought we were crazy, but it's okay. So, how does this work? Well, if you have a calorimeter, the heat that the calorimeter gains and the heat that the water gains, when you add those together, those are equal to the energy of the reaction. So your ham sandwich is burning, it gives off energy, so it's going to have a negative sign because it's exothermic, and the calorimeter and water are going to be endothermic, so they're going to have a positive sign. So that is the basic steps that we have to do to calculate the energy in the bomb calorimeter. Now, the other thing that's going to ask is how much energy per mole of substance. All right, so you just take that energy and you divide it by the number of moles of the substance you have. All right, starting here, it tells us we have 1 gram of table sugar, and it's burned in a calorimeter. Now, this calorimeter has 1.5 kilograms of water, which is 1,500 grams of water, and the calorimetry assembly has a heat capacity of 837 joules per degree Celsius. 1,500 calories. First of all, how do we convert that? We need to know the specific heat of water, which is 4.184 joules over grams degrees Celsius. And it tells us our temperature change is from 25 to 27.32, which is a difference of 2.32 degrees Celsius. And we're going to add that to the calorimeter, energy from the calorimeter, which we calculate by taking the specific heat of the calorimeter and the temperature change, 2.32. Okay, so if we do the math, we get 14,560.32 joules plus 1,941.84 joules for a total of 16,502.16 joules. That's the energy that the calorimeter's absorbing. So, what was the energy the reaction gave off? Well, it gave off 16,502 joules given off. So we have a negative sign. Now, it's customary to use kilojoules, so we're going to convert to kilojoules. There are 1,000 joules in 1 kilojoule. So we end up with negative 16.5 kilojoules released by the energy. How much sugar did we have? Go back to the beginning. We had 1 gram of sugar. How many moles is that? So we now have to calculate 1 gram of sugar divided by the molar mass of sucrose. Sucrose's molar mass is 342 grams per mole. So if I take 1 divided by 342, I get 0.00292 moles. Okay? We have kilojoules. To get kilojoules per mole, we just have to divide that by 0.00292 moles, and the number of kilojoules that 1 mole will give off is 5,643 kilojoules. And that's negative again because the reaction is exothermic. Okay? The next one, we're going to have to kind of work backwards. We know that the energy of the reaction is equal to the energy of the calorimeter plus the energy of, we don't have to deal with water in this one, so we don't have to deal with water. So the first thing we're going to do, and it's asking us to calculate the heat capacity. So first we're going to use the energy we were given and figure out how many moles that we used so that we can get the energy in the reaction. Okay? We had camphor. We had 0.1204 grams of camphor. The molar mass of camphor is 152 grams per mole. So that would be 0.1204 divided by 152, 0.000792 moles of camphor. Okay? And it tells us that that camphor had that amount of energy, 5,900 03.6 kilojoules for 1 mole. So we know we only had 0.000792, so we're going to multiply that to get rid of moles, 0.000792 times 5903.6 kilojoules per mole, and that gives us negative. Alright, and that value gives us 0.000792 times 5903.6, a negative 4.67 kilojoules, not per mole. Now we just substitute that back in to our reaction here. We know that the heat capacity, or the heat is negative, is 4.67 because that's what the calorimeter is absorbing, 4.67 kilojoules. We don't know the specific heat, but we do know that it's a 2.28 degrees Celsius switch. So we're going to take 4.67 kilojoules divided by 2.28, and the specific heat, therefore, will be equal to 2.05 kilojoules per degree Celsius. All right. Okay, see if you can do the next two. For number 3, you're going to have to, you're given heat capacity. There's no water in this one, so Q, the reaction is going to be equal to, the negative Q of the reaction is going to be equal to the Q of the calorimeter. You have your temperature, you have your specific heat of the calorimeter, so it's going to be easy to find the energy of the reaction and then divide that by the number of moles of quinine you had. So you'll take that divided by moles. For number 4, you've got the heat capacity of the bomb, you've got your temperature change, and you have water. So this one is going to be Q cal plus Q of the water. All right, and then you know you have 4.2 grams of ethanol, so you'll divide that by the molar mass of ethanol, and then take your answer here divided by moles. Okay? Sounds like a plan.